Welcome to this deep dive study session on Ethical Hacker Pro Module 15.2, focusing entirely on public key infrastructure, or PKI, designed specifically to get you ready for the exam. Moving to slide 1, titled, The Architecture of Trust Mastering Public Key Infrastructure, PKI, for Certification.
Yeah, it's great to be diving into this because, PKI is one of those concepts that sounds incredibly intimidating at first.
Oh, absolutely. The alphabet soup alone is terrifying.
Right. But its core purpose is actually answering a very basic, very human question. How do we trust a stranger over a digital network?
Like when you're doing something high stakes.
Exactly. Like when you wire your life savings to a bank online, PKI is the architecture that ensures you aren't actually, handing that money to a criminal in a basement somewhere. It manages the digital certificates and communication encryption so that every single electronic transfer is authenticated and secure.
And I really like the visual on this slide for that. It uses the image of a padlock and a certified stamp. That really gets to the heart of it, I think.
It does. It's the perfect analogy.
Because when we talk about high-stakes transfers, you obviously need the padlock, right? The encryption that keeps the data mathematically scrambled and secret from anyone trying to eavesdrop on the Wi-Fi.
Right, but the padlock alone is basically useless if you don't know who actually holds the key to unlock it.
Exactly. And that is where the certified stamp of approval comes in. That stamp is the authentication. It proves the entity on the other end of the line is actually your bank.
Yeah, because without both the lock and the stamp, the whole system completely breaks down. Like a lock without a stamp means your communication is completely secure, but you might be securely handing your passwords directly to a hacker.
Right. And a stamp without a lock means you know exactly who you're talking to, but everyone else on the network can just read what you're saying in plain text.
Exactly. So PKI is that invisible framework that brings those two essential features together into one cohesive, automated system.
Okay, so how do we actually build that system? Let's move to slide 2. PKI definition and exam traps. Okay, let's unpack this because the slide shows this giant umbrella protecting a bunch of servers.
Yeah, the crucial takeaway there is that PKI isn't just like one single software program or a solitary mathematical formula.
Right, it's a comprehensive security architecture. It's the whole umbrella.
And that umbrella concept is precisely where the exam writers are going to try to trap you.
Oh, they love doing that.
They really do. They'll offer these multiple choice distractors that sound super technical but completely miss the forest for the trees. So, for instance, a major trap is defining PKI as just an algorithm for encrypting and decrypting data.
Which it isn't.
Right. It utilizes algorithms, obviously, but it is not the algorithm itself.
Yeah, and another trap on this slide warns us not to confuse PKI with a protocol for secure key exchange, like RSA or Diffie-Hellman.
Yeah, that's a big one.
If I'm setting up a network, I might think, well, I'm using RSA, so I have PKI, but that's like saying I have a steering wheel, so I have a car.
That is a perfect analogy, yeah. Those protocols are just tools operating under the PKI umbrella. Another really common distractor is calling PKI simply software.
Right, because there's hardware involved too.
Exactly. Software manages the system, sure, but PKI is the overarching framework of policies, hardware, software, and the operational procedures.
It's the whole package.
It is. So as a mental exercise to really lock this in, here's an open-ended question for you to consider. In 2 to 3 sentences, how would you contrast a complete security architecture like PKI with a simple encryption algorithm?
That's a good one to pause and think about.
Yeah, consider the difference between the entire security apparatus of a physical bank versus, just the combination to a single vault door.
I love that. All right, to make all these moving parts stick in our heads, we are moving on to slide 3, translating the alphabet soup, the digital passport.
The alphabet soup, yeah.
PKI is notoriously full of acronyms that just completely blur together. But I love this slide because it maps the physical world to the digital world. Suddenly, it just makes sense.
Because our digital trust systems actually mirror the bureaucratic systems we've used for centuries, right, to establish physical trust.
Right, like the Registration Authority or RA.
Exactly. In the physical world, the RA is basically the post office worker who examines your driver's license and your birth certificate when you apply for a passport.
They're verifying your physical identity.
Right. So in the digital world, the RA is the entity that verifies the real-world identity of the person or the corporation that's requesting a secure certificate.
Okay, and then we have the CA, the Certificate Authority. So in our physical analogy, this is the secure government vault.
Yeah, because the post office worker doesn't print your passport right there at the counter.
Right, that'd be chaos.
They send your verified application up to the government vault, and the vault actually mints the physical passport. So digitally, the CA is the secure entity that mints the digital certificate.
Awesome. And finally, we have the VA, the Validation Authority. This is your border guard.
Exactly. When you travel internationally, the border guard doesn't issue you a passport. They just scan it,
Right. They check, is it real? Has it expired? Has it been reported stolen?
right, or revoked. Digitally, the VA does the exact same thing every single time your browser connects to a secure website. And what's fascinating here is that while this bureaucratic process of RAs, CAs, and VAs seems super heavy and slow in the physical world.
Like waiting in line at the post office.
Yeah, exactly. But the digital equivalent is totally transparent to the end user. It literally all happens in milliseconds behind the scenes.
It's incredible. Well, let's dig into the very first step of that process. Now let's look at slide 4, the Registration Authority, RA. The front desk.
The intake slot.
Right. This slide zeroes in on the RA. It accepts the registrations, it validates the identity, and it makes the decision to approve or deny the certificate requests.
And notice the slide mentions that in large enterprise environments, the CA actually offloads this initial enrollment processing to the RA just to save resources.
Separation of duties. Right. It's critical for scaling efficiently. And this slide actually gives us a great case study directly tied to an exam scenario.
Oh yeah, Robert's case study.
Yeah, we have Robert, an IT administrator, and he needs to acquire a digital certificate for his new company. The question is, what exactly does Robert need to provide?
Right, and the correct action listed there is that Robert must send identifying data with his certificate request to the RA.
But wait, if I'm Robert setting up this network, my first instinct would be to just send over my ASCII address
Yeah.
or my IP address. That proves exactly what machine I'm operating from. Why isn't that enough for the RA?
It's a really common point of confusion, which is exactly why it's such a big exam trap.
Yeah.
Think about what the RA is actually tasked with doing.
Validating real-world identity.
Exactly. It's verifying organizational identity, not network topology.
Yeah.
A MAC address is just a physical identifier stamped onto a network card by some manufacturer.
Right.
It proves absolutely nothing about whether Robert actually represents the company he claims to work for.
And an IP address can change dynamically anyway.
Yeah, every time a router resets. So all the RA wants is proof of who Robert and his company are in the real world. They want to see business licenses, domain ownership records, corporate documentation, stuff like that.
Okay, that makes total sense. So once Robert proves who he is, we need to actually mint the passport. Turning to slide 5, the Certificate Authority, CA. The mint.
The vault.
Yeah, the visual here is literally a vault minting a secure document. Let's dive deeper into what the CA actually does once the RA gives the green light.
So the CA is the ultimate trusted controller of the PKI certificates. Technically speaking, the CA is the specific computer or server that issues the certificate.
And mathematically, what is it doing?
Mathematically, it's taking the subject's verified identity and permanently binding it to their specific public and private cryptographic keys.
So it's locking them together.
Right. It creates this undeniable link between who they are and the mathematical keys they'll use to encrypt their data.
And there is a massive exam trap warning on this slide. It dictates a hard and fast rule you have to memorize. If a question asks what entity issues the digital certificate, the answer is always the CA.
Always.
Do not choose the RA because they only handle the intake and verification.
Exactly.
And do not choose the VA because they only verify validity later on. The CA is the mint. It is the only entity with the power to issue.
That is a critical distinction. Yeah, really commit that to memory.
All right, next up is slide 6, the Validation Authority, VA, the
Yeah.
border guard. Now that the certificate is minted and out there in the wild, the VA takes over the ongoing security.
Right, and the technical mechanism here relies on the X.509 standard and RFC 5280.
Okay, wait, let me stop you there. Those sound like the exact kind of dense technical terms the exam loves to throw at us to make us panic. What are X.509 and RFC 5280 actually doing?
Simply put, they are the universal rulebook.
Rulebooks, okay.
Yeah. For a digital certificate to be trusted by Google Chrome on a Mac, or Microsoft Edge on a PC, or Safari on an iPhone, everyone has to agree on exactly how a certificate is formatted.
Ah, okay.
So X.509 dictates the exact structure. It says, here's where the expiration date goes, here's where the name goes, here's where the digital signature goes.
Got it. And RFC 5280.
RFC 5280 is the document that outlines exactly how a system should read and validate that specific structure.
Oh, that makes sense.
Yeah, so when your browser connects to a hosted website, it receives their private key certificate. It uses those universal rules to check the certificate against the CA's information. typically routed through a VA.
Checking to ensure it hasn't expired.
Right, hasn't expired, hasn't been revoked, and that the name on the certificate perfectly matches the URL you actually typed into the address bar.
Okay, and the slide also has this visual of a blocked conveyor belt, which is warning us about another exam trap. A validation authority never accepts initial certificate requests. Its sole purpose is providing a service that verifies validity after a certificate already exists.
Which leads into an important thought experiment for you to consider. If you were to design a flowchart of a certificate request, why is it a critical security flaw to have the validation authority handle the initial intake?
Oh, that's a great question.
Yeah, think about the inherent risks of having the border guard also be the person deciding who gets granted citizenship in the first place.
Right, because if the border guard could just print passports right there at the checkpoint, corruption and fake identities would be instantly scalable.
Exactly. Separating those duties prevents a single point of catastrophic failure.
Let's check out slide 7, Certificate Management System, CMS, and Digital Certificates. We've talked extensively about the authorities, the RA, CA, and VA, but what is actually running all of this on the back end?
Right, the software.
Yeah, the CMS is the primary software component. It's the actual machinery of the PKI.
The CMS handles all the heavy cryptographic lifting. It physically generates the key pairs, like the public and private keys, that actually make the encryption work.
And it stores the host's private keys safely, right?
Yeah.
Which the slide notes is arguably its most critical security function.
Oh, without a doubt.
Right.
Because if that private key is ever stolen, the entire identity is compromised.
An attacker could just impersonate the server perfectly.
Exactly. And the CMS also distributes the public key out to anyone who needs to verify the host.
Now, on the other side of the slide, we have the formal definition for digital certificates themselves. They're described as electronic passwords associating the identity of a person or entity with that specific public and private key pair.
Yep. So just to summarize the flow, the CMS builds the mathematical keys. The CA issues the digital certificate that binds those keys to a verified identity, and that certificate acts as your digital passport moving forward.
Perfect. To make sure we have all these distinct roles firmly locked in, we are moving to slide 8, Diagnostic Matrix.
This is great for studying. It's a rapid-fire review table mapping the acronyms to their core functions.
Let's run through it quickly. Component 1, the Registration Authority, or RA analogy role, the front desk, core action, accepts and validates information contained within a request.
Right. And the exam distractor warning for that one. The trap is thinking the RA issues certificates.
Yeah.
It absolutely does not.
Okay, component 2, the Certificate Authority, or CA analogy role, the MINT, core action, issues, stores, and revokes digital certificates.
Now, the exam distractor warning here is a bit nuanced. Technically, the CA is the computer that issues the cert. But in smaller network setups, the CA role is often combined with the RA role on the exact same server just to save money.
Oh, I see.
But logically, they remain totally distinct functions. The exam will test you on their logical separation, so do not let real-world resource sharing confuse you.
Got it. And component 3, the Validation Authority, or VA analogy role, the scanner or border guard, core action, verifies the validity of an existing digital certificate.
And the exam distractor warning here, the trap is thinking the VA accepts initial certificate requests. It only checks existing documents.
Okay, slide 9 is titled 1, 2, 3, step, process the transaction phase. This kind of puts everything we just talked about into a chronological life cycle.
Yeah, it maps it out. Step 1 is the request, where the user or company applies to an RA.
Step 2 is the verification.
Right. The RA receives the request, verifies the subject's identity, and then formally asks the CA to issue a certificate.
And step 3 is issuance.
Yep. The CA binds the identity to the keys, issues the certificate, and critically, sends the updated validity information over to the VA so the VA knows this new certificate legally exists.
So what happens after all that setup? That is the transaction phase at the bottom of the slide.
Yeah, once the certificate is out there, the user sends it to another party, like, say, a customer trying to buy a pair of shoes online. That customer's web browser automatically checks with the VA. The VA compares the certificate against the CEO's official records to confirm trust. It's just a constant, ongoing background check happening every single time you load a web page.
But that background check only works if your browser knows who to trust in the first place, right?
Exactly.
Slide 10 gives us real-world examples. Major certificate authorities, CAs. The study materials highlight three major players you need to recognize for the exam. First is Komodo.
Yeah, Komodo's known as a general CA. They offer a super wide range of PKI services, particularly strong SSL encryption, available in 128 or 256-bit formats.
Okay, second is IdenTrust. They're described here as a vertical CA. What does it mean for a CA to be vertical?
A vertical CA specializes in specific, highly regulated industries. So IdenTrust focuses heavily on sectors like banking, government entities, and healthcare corporations.
Places with a lot of compliance rules.
Right. They have strict, legally mandated compliance requirements for identity verification. It goes way beyond what a typical retail site might need. So a vertical CA builds their entire internal infrastructure to cater exclusively to those specific, rigorous legal standards.
Okay, and the third one is GoDaddy, which is optimized as a commercial CA for both business and personal use.
Right. They're known for simpler services, transparent pricing, and providing certificates that easily comply with standard web browser guidelines.
Now, for a crucial distinction on slide 11, public CAs versus self-signed. We just discussed public CAs like Komodo or GoDaddy.
Yeah. And when you purchase infrastructure from those trusted authorities, your identity is vetted by an organization that the major web browsers like Chrome, Safari, Edge already have programmed into their root trust stores.
They already know to trust them.
Exactly.
Yeah.
Because the browser inherently trusts the public CA, it allows a direct, silent, secure connection to your website. The user just sees the little padlock icon and goes about their business without any friction at all.
But the other side of the slide covers self-signed certificates. These are created locally by a network admin using local infrastructure tools like Linux OpenSSL, Adobe Reader, Java's Key Tool, or Apple's Keychain.
Right. They generate the exact same mathematical public and private keys, but there is a massive catch.
Because you basically just vouch for yourself, right?
Exactly. You're vouching for yourself. So these certificates are inherently untrusted by public browsers. If you try to use a self-signed certificate on a public-facing website, the user's browser is going to trigger a terrifying warning page.
Oh, your connection is not private screen.
Yeah, throwing up red flags, warning the user that attackers might be trying to steal their information.
Which raises an obvious question. Why would anyone ever use a self-signed certificate if it causes those scary warnings?
Well, the use cases are actually quite common for internal operations.
Oh, like a closed network.
Yeah, if you have a closed internal corporate network or back-end servers that are only communicating with each other, public internet vetting just isn't required.
Right.
You control all the machines on the network, so you can manually configure your internal machines to trust your own self-signed certificates.
Which saves the company the considerable cost and bureaucracy of dealing with a public CA for traffic that never even touches the outside world.
Exactly. It's very efficient.
Let's apply this on slide 12, hacker case study. Kathy's internal network. This is drawn directly from the exam quiz.
That's a great scenario.
Yeah. The scenario is that Kathy refuses to purchase a digital certificate from a public CA, but she absolutely must establish a PKI for her local internal network. What should she do?
The slide shows the correct solution right away. She must create a local CA and generate a self-signed certificate.
Because it's internal.
Right, since it's entirely an internal network. She doesn't need external validation from Chrome or Safari. But we really need to systematically destroy the quiz distractors here because they target fundamental misunderstandings of how encryption actually works.
Okay, the first distractor trap suggests she should enable synchronous encryption.
Yeah, and synchronous, or symmetric encryption, uses the exact same key for both locking and unlocking data.
Like the key to your front door.
Exactly. PKI, however, is fundamentally based on asymmetric encryption, using a public key to lock the data, and a completely different mathematically related private key to unlock it. So synchronous encryption is entirely the wrong foundational technology for setting up a PKI.
Okay. The next trap says she should just ensure all HTTP traffic uses port 443. Now, port 443 is the universally recognized standard port for HTTPS secure traffic. So if she just routes everything through there, why isn't that enough?
Because a port is just a door in a building. Port 443 expects the traffic walking through it to be encrypted.
Right.
But routing regular plaintext HTTP traffic through that door won't magically encrypt it. The traffic will just fail, or it'll remain entirely in plain text for anyone to read. You need the digital certificate and the associated asymmetric keys to actually perform the mathematical encryption before it hits the port.
Okay. And the final trap suggests she should request a certificate from GoDaddy.
Right, but the scenario specifically stated she refuses to purchase one from a public CA.
And GoDaddy is a public CA.
Exactly. It violates the core constraint of her problem right from the start.
Putting it all into perspective on slide 13, the complete PKI ecosystem. This synthesizes everything we've covered using an e-commerce merchant scenario.
Yeah, imagine a new merchant wants to start selling products online securely. They can't just, spin up a self-signed certificate if they want anyone to trust them with a credit card.
Obviously not.
They have to undergo that arduous process of proving their identity with real-world business licenses and corporate papers to a recognized authority.
And the visual here shows this large, trusted authority box. For these high-stakes public environments, a single large company like Komodo or GoDaddy often acts as the CA, the RA, and the VA all at once from the perspective of the merchant.
Yeah, the merchant submits their papers to the intake desk, which is the RA. The authority verifies them, and their internal CA mints the keys. Then, when an end user visits the merchant store, the user's browser silently checks the authority's VA records in the background to verify the trust.
It creates a seamless loop of trust.
It does. Which brings us to our final synthesis question for you to ponder. Explain in 2 to 3 sentences why an e-commerce platform relies on a unified trusted authority rather than managing its own self-signed certificates.
Yeah, consider the immense friction a customer would experience if their browser threw a terrifying red security warning right before they were supposed to enter their credit card info.
Nobody's buying anything after seeing that.
No way. Finally, we arrive at slide 14, the ultimate exam cheat sheet. Let's do one last quick recap of the critical correct paths versus the trap alerts to cement this knowledge before you sit for the exam. Concept 1, PKI definition.
The correct path is remembering it is a comprehensive, overarching security architecture. The trap is thinking it's just an encryption algorithm or a single protocol like RSA.
Concept 2, verifying requests.
The correct path is knowing the RA accepts and validates the real-world information contained within a request. The trap is thinking the VA accepts requests. The VA only checks documents that have already minted.
Concept 3, issuing certs.
The correct path is that the CA is the only entity that issues certificates. The trap is confusing the CA's absolute issuing power with the VA's ongoing validation role.
Concept 4, applying for a cert.
The correct path is sending identifying organizational data, like business licenses, to the RA. The trap is thinking you need to send network identifiers like ANSI addresses, IP addresses, or specifying encryption algorithms during the initial request.
And concept 5, local network PKI.
The correct path is to create a local CA and use a self-signed certificate for isolated internal networks. The trap is thinking that just routing traffic through port 443 will encrypt it without a certificate, where that synchronous encryption is relevant to PKI.
Mastering those specific distinctions and the reasons behind them will navigate you safely through the PKI module of the exam.
Absolutely. But before we wrap up, I want to leave you with a final thought to mull over beyond just passing the test.
Okay, what's that?
Well, consider the sheer fragility of the modern internet. Our entire digital economy, every banking transfer, every private medical record, every secure email, it all rests entirely on the mathematical and bureaucratic rigorousness of these unseen certificate authorities.
It's kind of wild to think about.
It is. If a major root CA were to be fully compromised by a sophisticated threat actor like, if the mint itself was taken over, the foundational trust of the internet as you know it wouldn't just degrade, it would vanish in milliseconds.
Right.
The browsers would no longer know who is real and who is an imposter. And literally every secure connection would instantly become suspect.
That is a staggering level of responsibility resting on the invisible architecture we just explored. It really changes how you look at that little padlock icon in your browser.
It really does.
Well, congratulations on mastering these slides, and we wish you the absolute best of luck on your Ethical Hacker Pro exam.